Am I audible?
Yes.
Sir, I am on traveling, sir. Right now, I don't have a laptop, sir. I'm just listening.
Okay, no problem. No problem.
I'm connected to phone, sir. I'm
No
connected
problem. No
through
problem.
phones. Yes,
Yeah,
sir.
yeah, no problem. It's okay. You don't have to share. No problem. Okay. Okay. So 1 minute. Let me. So good morning, everyone. Welcome to the fifth session of Nonlinear Structural Mechanics using Python. So today, until this point, we have looked at So until this point, we first started with bar elements. We looked at mainly assembly code, how we assemble bar elements, enforce boundary conditions, and solve. Right. So if we look at overall what we have been doing in this workshop so far, we started off with bar elements. We looked at what is called an element stiffness matrix. Yeah, so we started with element stiffness matrix. Then we assembled several elements together in a certain fashion. And then we enforced the boundary conditions and solved. Then we looked at beam elements. We did the same thing. We derived the element stiffness matrix. We assembled it, and the assembly process was very similar. Only thing is it had 2 degrees of freedom per node and 2 nodes per element. Here also it was 2 nodes per element, but 1 degree of freedom per node. Right. So then we assembled and solved it. Third thing we did was we looked at truss elements. So truss elements, we said the element stiffness matrix in axis aligned coordinates. Right, so we looked at the element stiffness matrix in axis aligned coordinates is the same as that of bar elements. Is the same as that of bar elements. The reason is that truss is a 2-force member. So although in the global coordinate system we may have both u and v degrees of freedom, when we rotate the coordinate axis so that one of your axis is oriented along the axis of the bar element, then there is a degree of freedom and forces only along this, because a truss member cannot support transverse loads. So we said the element stiffness matrix in axis aligned coordinates is the same as that of bar elements. Then we used a transformation matrix. We used a transformation matrix to relate the local degrees of freedom to global degrees of freedom. And as a result, we got a relationship between the stiffness matrices in the global coordinate system and the local coordinate system as. So the stiffness coordinates in global coordinate system, we got it as, if we call the transformation matrix Q, it is something like Q transpose K local Q. Yeah. So K dash is for K local. Then this is what we called as the element stiffness matrix. Again, the next step was assemble boundary conditions, solve. So this part has been the same. The logic for this part, assemble and solution, assemble, boundary conditions, solve. This has been the same for everything from bar elements until now, and it will be the same for whatever. The next is plane frame elements, and the logic is still the same. You have a problem definition, then you have an assembly operation, and in assembly, what you do, you go over every element and then include the stiffness contribution from every element. So the next step is enforce boundary conditions. So boundary conditions has to be specified to the program in some systematic format, and then we solve it. After solving, you can also do some post processing to get the forces and reactions. So be it the frame elements or even continuum elements, two-dimensional plate and shell elements, or continuum finite elements, or three-dimensional finite elements, this part is going to be the same. Only the code for assembly may be slightly different, but the logic is the same. So the next topic in the workshop is plane frame element stiffness matrix. So a beam, we know it supports transverse loads. So this supports transverse loads. This bar supports axial loads. A truss member, a member only supports axial loads. Only axial loads. However, the truss itself can support transverse loads. So you can have a truss like this. So if you take a particular member, every member of the truss is axially loaded, but the truss itself can take transverse load. So truss is a two-dimensional structure, and so it has got 2 degrees of freedom per node and 2 nodes per element. Now coming to the frame, what we have is, so a frame element is something like a truss plus a beam. So it can support axial forces. It has an axial degree of freedom, and it also has lead transverse deflections and rotation. Okay, so this is what it is. So what we have is, we have a frame element like this, and let us say I don't have to draw it like this. I can put a frame element like this, and suppose I orient the coordinate axis along the axis of the frame element. Say I have coordinate axis like this, x dash y dash, and I have the global coordinate axis like this. X, y. Now in the x dash y dash coordinate system, let me use a different color. I can have degrees of freedom. So this is node 1, this is node 2, and I can have degrees of freedom along this axial direction. I can call it u1 dash, v1 dash, and this point can also have a rotation, theta dash. Similarly, this point can have a u2 dash, v2 dash, and a rotation, theta dash. So correspondingly, we also have the forces. So if you draw another, yeah, so that you know. So the degrees of freedom are u1 dash, v1 dash, theta 1 dash. Sorry, this is theta 1 dash and theta 2 dash. And you have u2 dash, v2 dash, theta 2 dash. And forces are f1x dash, f1y dash, m1 dash, m is the moment, and corresponding to this, you have f2x dash, f2y dash, M2 dash. Now, can we relate these two? So this, as I said, is a combination of a truss element and a beam element. Therefore, if we look at the element stiffness matrix in the primed coordinate system, it is something like this. So, element stiffness matrix. Or first, let me say element stiffness relations in x dash, y dash coordinate system. Let us suppose this has got axial stiffness AE and flexural rigidity EI, and the length is L. So what is the relationship between F1 x dash and say U1 dash, U2 dash? So how is F1 x dash related to U1 dash?
A by L times of U1 dash.
Okay. Is it positive or negative?
Positive.
Okay. And here?
Minus AE by L times of U2 dash.
U2 dash. Okay. So does it depend on V1 dash? So if this element has got a lateral deflection V1 dash, that is not going to axially stretch the element under small deformation assumptions. So under this is important. If you consider infinitesimal deformations, V1 dash will not result in a F1x or F2x dash. Right, so the axial and transverse degrees of freedom are completely uncoupled if you consider that the deformation is small. So if this moves laterally, the element is going to undergo a slight stretching, but that stretching is very small compared to the other forces. Therefore, it can be safely ignored. Similarly, F2x dash, you can write this as minus AE by L U1 dash plus E by L U2 dash. So given that V1 dash, theta 1 dash, V2 dash, and theta 2 dash do not affect the forces applied at these two ends, you can fill it up with zero coefficients. So you can say it is plus 0 V1 dash plus 0 theta 1 dash. And you have here plus 0 V2 dash plus 0 theta 2 dash. Similarly, here you can fill it up with plus 0 V1 dash plus 0 theta 1 dash and plus 0 V2 dash plus 0 theta 2 dash. If you put them together, what do you get? You have F1 x dash, F2 x dash is nothing but AE by L
0, 0,
0, 0.
minus AE by L 0, 0.
Yes. Then you have a minus AE by
0, 0 plus AE 0, 0.
Here you have the full degrees of freedom matrix. Let me call it D. Right. So D matrix is nothing but the entire set of degrees of freedom. U1 dash or D dash. I'll call it D dash. U2 dash. Sorry. U1 dash, V1 dash, theta 1 dash, U2 dash, V2 dash, theta 2 dash. Okay. So what you observe is that corresponding to the degrees of freedom where you have an action, you have the corresponding bar element stiffness coefficients, and in other places we just have a 0. Similarly, for the beam part, suppose you have a beam. Oh, so these F1 y dash, M1 dash, F2 y dash, and M2 dash are the beam. They come from the beam relation. So if you say F1 y dash, it is something times V1 dash plus something times theta 1 dash plus something times V2 dash plus something times theta 2 dash. So this, I think it's 12 EI by L cube. This is
CI by L square.
L square. And this one is minus 12 EI by L cube.
Minus
And here you have, no, it's plus 6 EI by L square.
plus 6 EI.
Sorry. I think it's plus. Yeah, plus 6 a by L square. I put it on the right hand side, 6 ei by L square. Bad. So this is fine. I'll just give the spacing appropriately. Theta 1 dash plus something times V2 dash plus something times theta 2 dash. So this is 12 ei by L cube, 6 ei by L square minus 12 ei by L cube and 6 ei by L square. So again, you can fill it up with 0 coefficients. So you can add a 0 u1 dash and 0 u2 dash. So this is a beam equation and it depends only on, so here you said 0, 12. I'll take the E by L cube out. 6L, 0, minus 12, 6, yeah, minus 12, 6. So this multiplied by D dash, where D is the full set of degrees.
6L, sir.
6L, 6L, yes. Yeah, so this is the full set of degrees of freedom. So correspondingly, you can do this for every row. Now, what is the stiffness matrix? It has to relate F1x dash, F1y dash, F2x dash, sorry, M1 dash, F2x dash, F2y dash,
M2 dash.
M2 dash. Now this is related in some fashion to this full degrees of freedom matrix. I'll call it D dash. Now, so we saw that in the first row, we just have an AE by L 0, 0. So this is the first row. This is basically the first row. We have 0, 0 minus AE by L 0, 0. Similarly, F1 x dash we got 0
minus
12 F1 y dash.
Okay, sir.
So this is F2 x dash. What we have here. Yeah, this is F2 x dash. That is the fourth row, not the second row. So here we have 12 EI by L cube, 6 EI by L square. This is this row, 0. And then you have minus 12 EI by L cube, 6 EI by L square. Similarly, third row you can fill up. Fourth row, as we saw, it is minus AE by L, 0, 0, AE by L, 0, 0. Similarly, other rows you can fill up. So if you look at the pattern, it is that it is just you are putting together the beam and the bar stiffness matrix in a special manner. So along in the beam rows, so it's in beam rows, which are rows 2, 3, 5, 6. Right? In beam rows, bar coefficients are 0. Right? So in rows 2, 3, 5, and 6, coefficients 1 and 4 are 0. In bar rows, which is rows 1 and 4, the beam coefficients are 0. The beam coefficients are 0. Apart from that, put the matrix as it is. So if you do that, we'll get a matrix like this. So in the axis aligned coordinate system, we are the stiffness matrix K dash is just A by L 0, 0 minus A by L. So you just combine the two stiffness matrices in this format. So this is the full degrees of freedom matrix D dash. This is the full force vector F dash. And this is what relates them, which is K dash. This is the element stiffness matrix in the local axis aligned coordinates. So, okay, so this is fine. I'm just checking if, okay. Next, what do we do? So next, this is in the axis aligned coordinate system. So we have to transform. So again, transformation relations are also the same. There's no change from the truss. So we need to transform. How are F1x and F1x, F1y? How is it related to, or F1x dash, F1y dash? How is it related to F1x and F1y? This we saw last time. So this is a couple of forces, and you have something like this. this f1x, f1y. This is f1x dash, f1y dash. So what is f1x dash?
Cos
F1,
alpha f1x plus sin alpha f1y.
yeah, if the angle between them is some alpha, it is cos alpha, sin alpha, right? So you just resolve these two along f1x dash direction. So it's like, sorry. So you have a vector like this. Yes, and then this part is f1y.
f1y is minus sin alpha f1x plus
Minus.
cos alpha. Cos
Yes.
alpha f1.
Yes, so this is correct. So this angle will also be alpha. So it is cos alpha f1y plus minus sin alpha f1x, because this is 90 plus alpha. This angle is 90 plus alpha. So this you can do. Now you're just adding one more component, which is the moment. So I'm just extending the stiffness matrix, the force vector, to include one more, which is moment. So this will become, you'll get a m1, and here it is m1 dash. So this is 3 cross 1. This is 3 cross 1. So by matrix multiplication rules, this has to be 3 cross 3. Now, can the forces depend on the moments? No, the forces do not depend on the moments. So now let me make a slight change here. So this matrix is going to remain unchanged.
The remaining elements will be 0, sir.
Yeah. So this is going to be retained. You have to be careful. Remaining elements, all of them will not be 0, right? So if you have so up to this point, it's fine. So just as we did for the stiffness matrix, f1x dash does not depend on m1, so this has to be 0. f1y dash does not depend on m1, so this will be 0. So m1 basically is you have a moment at this point, which is m1. If you
0,
rotate,
0, 1.
yeah, if you rotate the coordinate axis, the moment will not change. It will remain the same because the moment is in the same plane as the rotation. Therefore, this will be just 0, 0, 1. Therefore, this is our transformation matrix per node. So this is the transformation matrix Q per node. But in general, even this is not a full transformation matrix. We have a 6 cross 1 matrix, right? So we have a 6 cross 1 matrix. So this first 3 degrees of freedom for node 1, the third, let's say next 3 degrees of freedom for node 2, and this in the global, this in rotated coordinate system is related to the same values in the unrotated coordinate system as. So this you can say 1 dash and 2 dash is related as what? So 1 dash is related to 1 by the above matrix, and 1 dash is not related to 2. So forces at a point are related by transformation. The force at node 1 cannot be affected by forces at node 2. So these are all 0. So if you partition this matrix, these are all 0 elements. Whatever relate degrees of freedom at node 1 to the degrees of freedom or the forces at node 2 are 0. So these two, all these, this 9 plus 9, 18 elements are 0. And here what do we have? This comes here. So this, whether it is node 1 or node 2, they are related. The global local relations are the same. So this goes here and this goes here. So if you look at the transformation matrix, it will look like this. Just like the truss element. In truss element, we didn't have this. Okay, what have I done? So this says this
1
wrong.
and 1 will come now,
Yeah,
sir.
this should be 1. This should be 1. Yeah. Yeah, I'll correct it and I'll upload it on the classroom page. Yeah, this I'm wrong. This has to be 1 and 1. Now, it is also wrong. This has to be, ignore this. So Q, it's wrong. So I'll write down the right expression here. So the transformation matrix for frame elements it is 6 cross 6 because frame elements have 3 degrees of freedom per node and 2 nodes per element. And suppose you say C is cos theta, S is or alpha, C is cos alpha, because theta we are using for the degrees of freedom. S is sin alpha, then Q is cos alpha, sin alpha 0, 0, 0, 0, sin alpha, cos alpha 0, minus sin alpha, cos alpha 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, cos alpha, sin alpha 0, 0, 0, 0, minus sin alpha, cos alpha 0, 0, 0, 0, 0, 0, 1. So this is the right transformation matrix. Right? The rest of the steps are the same. So we say f dash is equal to qf, u dash is equal to qu, or d dash is equal to qd, right? So d dash is equal to qd, and f dash and d dash are related as f dash is equal to k dash d dash, which means qf is equal to k dash qd dash, but Q is an orthogonal matrix, so Q transpose Q is equal to identity. So pre-multiply Q transpose on both sides. So we get Q transpose Q, which is identity. Identity acting on F is simply F. That is equal to Q transpose KQ. Okay, this is there's no dash here. It's QD. Yeah. So I have substituted D dash is equal to QD here, so there's no dash there. Right. So this gives the relationship between the global forces and the global degrees of freedom. So this matrix is nothing but the global stiffness matrix K. Sorry, element stiffness matrix in the global coordinates. So this K is given as Q transpose K, K dash Q. So this is the same as the truss element. Only thing is the Q matrix has a 0, 1 row appended to it. Otherwise, it is the same. So this is fine. The matrix is wrong. So the matrix you can look for is this. So we are already we are set. We can solve the problem now, and let us discuss the algorithm first, as usual. So what is the first step? Now you will be able to tell. Yes. And what is the kind of inputs I need to give? Nodes. Nodes will be of the form x1, y1, x2, y2, and so on. Then LMs. That will be what? That will be the connectivity. So it is node 1, node 2. So it's like node 1 of first element, node 2 of second element, and so on. Sorry, node 1 of first element, node 2 of first element, node 1 of second element, node 2 of second element, and so on. Then we need, what do we need? AE, EI, those will be given. Then, so this assumes same for all elements. If it is not the same for all elements, you should also give a matrix like AE for first element, AEI for the first element, then AEI for the second element, and so on. So that can also be done. Then main thing is boundary conditions. So how do we do that? Boundary conditions. How did we specify last time? So here we have 3 degrees of freedom per node. So again, we'll give it as a matrix. So can you recall how we did last time? Okay, maybe your voice is very low. That's why. So node number. So it's like last for the beam it was displacement rotation. For the truss it was U1. For the truss it was horizontal and vertical displacements. Here it is horizontal displacement, vertical displacement, and rotation. So in general you can just call it as for DOF1, DOF2, and DOF3. Right. So this is U, this is V, this is theta at every node, and this we can specify. Then we have to give loads. So loads also you can either give it in this format or you can give the entire load matrix as it is. Or then the next step is okay. Sorry, I'm not able to hear you. It's very low. Maybe you can check your audio device, that mic or your headphones that may be loose. So this second thing is assembly. And if you look at the logic for assembly, so there are 3 degrees of freedom, and we take elements of, so we're going to put elements like this together. So this element will come here, and this element will come here. So the first node of element goes here, this goes here, this goes here, and this goes here. So this logic is something like the global stiffness matrix of something is equal to, or last time as Dharni suggested, there was this plus equal to notation. It is plus equal to local stiffness matrix of something. But what is the logic here? There are 3 degrees of freedom per node. So what should be the thing here? For every degree of freedom, suppose node 1 is first node of the current element. And node 2 is second node of current element. Then what do we do for every element? Okay, it is still very faint. I can only hear you're telling something, but I'm not able to get what it is. Is it the same for others also? Or is it a problem with my system? I'm not sure. Is
Node 1, comma node 2.
no, it's not node 1, comma node 2. So for every node, you're having 3 degrees of it. Sorry? If you're saying 2 times node 1, it's not correct. Yeah, yeah, we can hardly hear you, but I can hear the others fine. Maybe you can also join the same meeting from your mobile for audio. That's allowed. So it's like Teams allows you to join simultaneously on your computer and your mobile. Maybe that will help with the audio. So if you say 2 times node 1, it's not correct, because if you look at the logic, this is global node 1, global node 2, global node 3. So if you say U1, V1, theta 1 are here, U1 will go to global degree of freedom 1. V1 will go to global degree of freedom 2. Theta 1 will go to global degree of freedom 3. Then if you look at the second node, if you have U2, V2, theta 2, U2 will go to global degree of freedom 4. V2 will go to global degree of freedom 5. Theta 2 will go to global degree of freedom 6. So if you look at the logic, local, so these are the local degrees of freedom, right? So local degree of freedom I goes to global degree of freedom because you have 3, it is like 3 times node 1 plus I, right? You agree? So if you say local degree of freedom I at node 1 goes to global degree of freedom, it goes to global degree of freedom 3 times node 1 plus I, because when you go to node 2, the degree of freedom will start with 4. When you go to node 3, the degree of freedom will start with 7, because for every node you are having 3 degrees of freedom. And in Python notation, if you say, it's like locally you have degrees of freedom 0, 1, 2 at every node, at every local node. So if you recall, what do? We take local node number, which is either 0 or 1, that goes to global node number, which is, let me call it node 1 or node 2. Now, if I say node 1 has got 3 degrees of freedom. So if I say if I say nth global node, it has got n minus 1 degrees of freedom, n minus 1 nodes before that, which means 3 into n minus 1 degrees of freedom are over already. 3 into n minus 1 degrees of freedom are over. They are already taken. So your degree of freedom will be 3 times the current node number plus 1. So in Python, as you know, node 1, if you mention it in Python format, the numbering starts with 0. So this node 1 will have node 1 degrees of freedom before. So it's like if you take if you'd say Python number 3, it will already have 0, 1, and 2 before that. There'll be 3 indices before 3 in Python. Therefore, the logic here is, if you take a local degree of freedom, if you say, so if you say P and Q, right? If you say local degree of freedom P and Q will go to 3 times node 1 plus P and 3 times node 1 plus Q, something like that, right? So if you take the first, it was okay. So the logic is you take, if you take the first element, first degree of freedom will go to 3 times corresponding to 1, it is node 1, and P is equal to 0. So it is like 3 times 0 plus 0. So it will go to 0, which is global node 1, degree of freedom 1. If you take the second degree of freedom, it is node 1. So it is 3 times node 1 is 3 into 0 plus P is equal to 1. So this will go to global 1. Now, if you take the local degree of freedom 5, which is V2, that will be like, it is 3 times, it is a node 2. So it is 3 times node 2. Plus in this order, what can P take? P can take only 0, 1, 2. So it is 3 into 1 plus 1. It will go to global degree of freedom 4. So 4 is actually 5 in Python. So that is how we assemble it. Then once we assemble, then we enforce boundary conditions. So if you have node number and something restrained, so we gave it in this format: node number, true or false, some true, false, true, something like this. So if it is true, if something is true, then you make everything in that row, everything in that node, everything in that row 0, right? So you say, you find out the row ID, what is the row, and then you say everything in that row, you set it to 0, except the diagonal entry. So you make everything 0, and then the diagonal entry you make it 1. So this is how we enforce the boundary condition. Effectively, what it does, if I want to set some u4 is equal to 0, what it does in the stiffness matrix, everywhere else will have the stiffness coefficients. In row 4, we'll have 0, 0, 0, 1, 0, and you will have the stiffness coefficients everywhere else. So this multiplied by u1 up to u4, then all u1 is equal to 0, means corresponding to u4, we just have the equation u4 is equal to 0. We don't have the equilibrium equation because we don't know the reaction. If we set some displacement degree of freedom 0, it means there is a reaction there, but we don't know the reaction force which we have to supply on the right hand side. So instead we cut down that equation and replace it with u4 equal to 0. And finally we solve. We solve as A inverse U. So this is like K reduced. Sorry, what happened? U F. U is equal to K inverse. So this is very much similar to what we have done so far. Only thing is, since we have 3 degrees of freedom, instead of 2 times node 1 plus P in the truss program, we'll have 3 times node 1 plus P. Now I can look at this problem. So we can solve this problem. So solve for all the nodal displacements and the reaction in the given frame. So first let us code it. Let's write down the general code. Then we can check with the analytical solution. So I have already shared it. You can make a copy. So this is the one. Right, again, I have given you a plotting function so that you can visualize the solution that you get, but you don't have to worry about how it works. Yeah, so to make it more interactive, one of you can share your screen, and so it'll be we'll know. I'll also get an idea of how much you have been able to follow. So yeah, I'm not really sure you had the chance to, because I didn't send any homework or anything, because I'm not sure you had the chance to go through this yourself. And we have only one or two more sessions left. So I think this is the time for you to code it yourself. So maybe you can take turns and you can share your screen, and you can code. So okay, I'll stop sharing. One of you can take it over, and I'll help as if you make any mistakes. And all of us can pitch in. All of us can give suggestions. So just as when I do, you tell, right? So one of you can share and we can. Anyone, doesn't have to be the same person also. So maybe assembly one person can write, then transformation element you can write. Yeah. Okay, so you can go to the first function.
Am I audible?
Yeah, you're audible.
Whether should I go for this plane frame element stiffness matrix?
Yes. So you can write down the first function. Let us see. So this has to return. So what are the steps here? First, you have to get the stiffness matrix in axis aligned coordinates, then use a transformation matrix, and then transform it to the global coordinates. So you start with the you can start with the frame stiffness matrix for in element coordinates. You can refer to the function above that, truss element stiffness matrix. You don't need nodes. We are dealing with one element right now, right? So this will take in so AE, so AIL, alpha and E are already given, right? So it just has to return that matrix, that 6 cross 6 matrix that I showed. So just take everything as given. So you see the arguments of the function, it is A, I, L, alpha and E, right? So whatever it has to return should depend only on these. You don't need nodes. You don't need anything else. So it just get started. That 6 cross 6 matrix, right? So in the first row, 2, 3, 5, 6 entries are 0. Yeah. So this is K dash, I guess. Yeah. I can tell you the coefficients AE by L. In fact, others can also tell. So others can also help your friend. Is that right? Can anyone say? Is that all right? Yeah. Yes. Then 0. Yeah. Second degree of freedom is displacement at node 1. So 12 star I by L. Yes. Comma. Yes. Six star E star I by L square L star star 2. Comma. What should you get? So it's the fourth degree of freedom in second row. So it should be 0. It is the actual degree of freedom. 0. Then minus 12 star E star I by L cube. Comma. 6 star okay. Next is 0. 6 6 E I by L square 6 star E star I by L star star 2. Zero minus 6 star E star I and then 2 star E star I. Yes. You need a comma there, yeah. Yeah. Why is it 0? Yes. You can copy paste the first row and just delete the minuses. It's faster, right? Yeah, so first will be minus AE by L. Fourth element will be AE by L, comma. And copy paste the second row. And make it negative. Negative. Yes. Yeah, and copy paste the third row and just swap the 4 and 2. Okay, very good. So this is K dash in the local coordinate system. But can you do matrix operations with this? What is the data type here? Is it a matrix type or? Yeah, a small. You have to make it small.
Is it correct, sir?
I have to use the parenthesis, like normal brackets. Yeah. Now it's correct. So this is in the local coordinates. Now you need a transformation. So this is step 1. So you can use comments very well because comments after that when you read the code yourself, it will be helpful. Now you can write a comment transformation. So for comment you can use that hash. Yeah, say transformation. Okay, then so what is required for transformation? You need cos alpha, sin alpha. So if you don't want to write cos alpha, sin alpha, you can use that C is equal to NP dot cos alpha. Yes. Yes. Check that indentation. There seems to be an extra gap, right? So K dash is at one different level and C, S, Q are at a different level that you may have to correct. Now you see K dash, just put a tab in front of K dash, like add a space in front of K dash.
No, it's fine.
It's fine. It's fine. Okay. Okay, how come it is suggesting all the code?
Sir, it's AI.
Oh, okay. Okay, so this. Mm, yeah, so this part, okay, you don't need to follow what it suggests, but it's fine. So this is Q, this is fine. Q dot T dot K dash dot Q is fine. Yeah, so Q dot T is, I think, the transpose, but you can also write it explicitly that NP dot transpose dot. Yeah, so it is NP dot transpose dot Q dotted with K dash. Now this K dash has to go, the bracket after K dash has to come after dot Q. So you multiply K dash to Q and to the product you're multiplying Q transpose. So the bracket after K dash has to come after dot Q. Yes, so this is fine. This is correct. Okay, so yeah, this is the element stiffness matrix. You're doing Q transpose KQ and therefore it returns and you're returning it. Very good. Next step, you have to assemble the global stiffness matrix. So what are the things that you need here? So here you only have access to nodes and elements. You can look at the truss problem, what you have done. You can use the same initialization. You can copy paste it. What is the size of K here?
6 cross 6.
No, it's not 6 cross 6. It is the global stiffness matrix. So it is 6 cross 6 is element stiffness matrix.
Yes, size.
So the size K for truss, we called it 2 times number of nodes. Why is it 2 times number of nodes? Because we have 2 degrees of freedom per node. Here, what should
So
be the
it
size?
is 3 times number of nodes. 3 times
Sorry?
number of nodes. 3 times number of nodes, sir. Order of 3 times number of nodes.
Yeah. So you can correct it in. Yes. Then we have initialized it. What is the next step? This is also not going to change. So loop over elements, that for loop will be the same. Okay, then. So where do you think the change will come? These are all fine. So you're only you're identifying the current element, looking at what is its first node, what is its second node, and then length of the element formula is not going to change. The orientation will not change. So then instead of calling truss stiffness, you have to call the frame stiffness, right? Okay, so you call the frame stiffness there. Don't copy paste this. The arguments are different, right? You have both A and I appearing here. So it's not just AE. It should be in the same order. Yeah. AIL alpha E. Yeah. And there's an extra space before K that should be corrected in, right? Because Python gives that it's sensitive to such small. No, you have to push it a little ahead. So L alpha, these are in the same level. That deal with the current element comment, yeah. That can move a little bit. The first comment, deal with the current element comment is there, right? That has to move a little front. Anyway, comments don't mind, they won't affect the result, but still it's difficult to read the code otherwise. Yeah. Yes. Okay, now we get the frame stiffness. Then what should we do? Now somebody else also can. Now somebody else can. You can copy paste this part, but we have to. Don't change the truss problem file.
Okay, sir. Should I copy this? The remaining?
Yeah, you copy paste up to return. Then we'll discuss. There has to be some changes. We'll discuss that. think it's okay. Okay, so yeah, so one of you can tell me what is the range of P? P should be in which range? 2, 3, 4. So we are calling the local node numbers as P and Q. So what should be the range of P?
3, sir.
Should it be 3? Because P is like local node number, not the local degree of freedom. So there are only 2 degrees of freedom, 2 nodes per element. So it is only range is fine. It is P in the range 2 and Q in the range 2. That is correct only. So that doesn't have to be changed. Okay. So you see what we are doing? We are multiplying 2 times P and 2 times Q, right? So that's because P is the node number. P goes from P is like first node and second node. See, node 1 is current element of P and node 2 is current element of Q. So if P takes the value 3, then the element matrix has only 2 columns, right? For every row, there is an element node 1 and node 2. You cannot have P exceeding 2. So the range is actually fine. P is in the range 2 and Q is in the range 2, which is like P takes the value either 0 or 1 and Q takes the value 0 and 1 in successive loops. So that is fine. And the global node number relation is also fine. So what is current element? Where are you getting it from? You can scroll up. Right? Current element is ith row of the elements array. Okay, so that is fine. So ith row of the element array is current element, and in the current element, 0th entry will be node 1, first entry will be node 2. So you come down, you see how you are getting the global node number. You're referring to that elements array and then getting node 1 as the global node number of the 0th element, node 1 of current element. Node 2 is global node number of second node of current element. Okay. Now look at the now you can delete those 4 or you just comment out the 4 these things, 4 sentences after plugin. Yeah, you can comment out the 4 lines after plugin. We'll write it in a more concise format. Okay, so yeah, shortcut for commenting on collab is you just do control and // So the one below question mark, right? That one you just do / that will comment out in a. Now we can enter after plugin. Okay, so what is the logic now? Yeah, go up after plugin. You can start typing. You just give the placeholder. Somebody else or you yourself, you can say the logic. First type the placeholder k of square bracket capital K of capital K. It's the global full structural stiffness matrix. Capital K of square bracket something comma something. Yeah, you just put a comma is equal plus equal to small k of something comma something. Yeah. Yeah. Now one by one you can tell me. Yeah, you can take turns and tell me what should come in the first argument of this one. You start from the right hand side. That's easy, right? You're saying 3p plus 1. Start from the right hand side. So p is in the p can take only 2 values 0, 1. Why is it p comma q? What is the size of the local stiffness matrix? Element stiffness matrix. What is the size of the element stiffness matrix?
6.
6 cross 6, right? So how many? So how many entries have to be plugged in? 36 entries have to be plugged in for every element. And So how do you do that? So you have to think a little, right? In the last case, we had 2 degrees of freedom per node. So for the beam or for the truss, we had a 4 cross 4 element stiffness matrix. So it was like 16 entries. And we had this P and Q in a loop. So 16 by 4, we had 4 lines. Here you need to plug in 36 entries. 6 cross 6 is 36, and P and Q are in a loop. So divide by 2, divide by 2. So you need to write 9 lines, right? So for every node, there are 3 degrees of freedom. And these 3 degrees of freedom will interact with 3 degrees of freedom of the other node, right? 3 degrees of freedom of the first node with the 3 degrees of freedom of the first node, 3 degrees of freedom of the first node with the 3 degrees of freedom of node 2, and so on. So there'll be, I know there is no another comma. You can't have another comma. It's all 2-dimensional matrices, right? You don't have another comma. It has only 2 indices. There's a row and there's a column. So, so let me tell you. So it's like, if you recall what I wrote in the slides, this P and Q are node numbers. And for every node, you have 3 degrees of freedom. So you can say 3 star P and 3 star Q. First one will be 3 star P and 3 star Q, right? Look at the previous code. We had 2 star P and 2 star Q as the first entry. So on the right hand side. No, on the right hand side, not on the left hand side. Yeah, it's 3 star P and 3 star Q. Right? You have to look at the logic. You look at the pattern last time. What did we do? So it's 2 star P, 2 star Q. And on the left hand side, wherever you have P, you have a node 1 and node 2, right? Wherever you have P on the right hand side, you have node 1 on left hand side. And wherever you have Q on the right hand side, you have node 2 on the left hand side. That is the local global mapping. So here also it's the same logic. It is 3 star node 1, comma 3 star node node 2. Right? So this is okay. But you have to do it how many times? You have to do it 9 times. So 3 star P will have 3 star Q plus 1, 3 star Q plus 2. Then you have 3 star P plus 1 with 3 star Q plus 1, 3 star Q plus 2. Okay, don't copy paste. Is there a simpler way of doing it? Think about it. So here PQ plus 1, P plus 1 Q, P plus 1, Q plus 1. That was the idea in truss problem. Now it will be PQ plus 1, PQ plus 2, then P plus 1 Q, P plus 1 Q plus 1, P plus 1 Q plus 2, then P plus 2 Q, P plus 2 Q plus 1, P plus 2 Q plus 2. So you have to type 9 lines, but don't type the 9 lines. When you feel you are writing something repeatedly, use a loop, right? Now, what is a loop over? You can write a loop. So after plugging, you write a loop. For, yes, correct. Again, yeah, okay. You can follow that. R in range. Range should be correct. Is it 2 or 3 or whatever it is? You can see. S is also required. Let it be. S is actually required. So I said it's P plus 1, P plus 2. So it has to take 3 values. So range has to be. Yes, range has to be 3. Right? Then indentation, you have to take care. Yes, until now you are right. Yes, one more indentation. It has to come inside the for, so indent it further. And remove the extra space above it. So you have got 3 into node 1 plus R, 3 into node 2 plus S, plus equal to 3P plus R, 3Q plus S. So as a quick check, you have to you can check, right? You have to plug in 36 entries. The local element stiffness matrix is 6 cross 6, and you have 36 entries. So you see the total, you have one line of code. How many times it repeats? See the number of for loops. So you have loop for P, Q, R, and S. And how many times? 3 times 3 is 9. 9 times 2 is 18. 18 2s are 36. So this line of code is being repeated 36 times. And it takes care of it, right? All the 36 entries will get plugged in appropriate places. So very good. This is the end of assembly. Next, what do we do?
Return K.
Yeah, return K. Write it. Okay, so can you go down to the assemble part? Okay. So what happens if you put return K inside the loop? It will return every time, right? Which means it will return after the first iteration. Once you write a return K, the function will be exited. So return statement should be outside all the loops in a function. So return is already there. When you copy paste it, it's already there. Now you can delete those comments. Those junk comments can be deleted. Those 4 green color lines we can delete. Okay, so this is fine. Just check the indentation of your return statement. Is it at the same level as the first for loop? It is not, right? Okay, no. First for loop is not the P loop. It is above that. It is the element for ILM in current LM, something like that. For II, yeah, it should be at the same level as that. No, wait, that's a problem. So this P and Q are going on in every element. So this for loop has to be inside. Okay. So this every line after for P in, that has to be at the same level as K is equal to frame stiffness. Yeah, that for P in the range 2, right? For P in range 2 should be at the same level as K equal to frame stiffness. No. Don't get confused. See, Q is a loop inside P, right? So whenever you have a for loop, everything that comes after that should be indented. So this statement for P, yeah, you have to 1 minute. You can do one thing. Yeah, when you run this, there'll be some issues. That's why I'm okay. So you don't have this. Okay, you do one thing. You just go to the beginning of this assembly function, right? So I have this.
Yes,
Yeah. So just clean up the indentation once. So after that, in front of the first line, press a tab. Keep your cursor in front of that comment initialization. Initialization. Keep your cursor before that first hash. No, just before the first hash. Yeah, press a delete. Yeah, come down. For loop over elements, move it to the right. that comment has to be a little right. Before the hash. Okay, then come down to the deal with the current element, move it to one step back. No, it's too much. Just press one delete. No. Don't backspace, just delete. It should be at the same level as current. No, it's not correct. You have to move the hash to the level of currents. Move, yeah. Now go to the next one. Delete one space before that. Okay, come down. Come down to this. Let us call local numbers PQ. Move it one step back. Okay. Now for P in range 2, move it one step front. For Q in range 2, move another step front. Okay. Now this return statement has to be one step back. Yeah, I think it's okay. Yeah, just check this return statement is at the same level as the first for loop, which is for II in range. Yeah, these two should be at the same level. Okay, so okay, now it's fine. If you feel they're in the same level, it's fine. It will work. Okay, the next step is boundary conditions. So okay, before we write the boundary conditions, you can have a problem first, right? So can you give the inputs for a cantilever beam? Okay, so cantilever beam, but the cantilever is vertical. So let me share my screen once. I'll just tell you the.
Sir, it stops. If it stops.
Sorry, what did you say?
At a time, 2% can share.
Again, your voice is not clear.
Sir, should I have to stop sharing my screen so that you can share?
That's not a problem. If I start sharing, automatically yours will be unshared.
Okay.
Yeah. Okay. So this problem will come a little later, or you can also start with this. So this is the problem. Okay. So you have, or you can tell me the inputs here. Then you can just type. Right. I'll send a screenshot somewhere. So what is the nodes matrix? Sorry. Yeah. I'll say this is node 1, node 2, node 3. What is nodes matrix? Yes, somebody can.
0, 0.
Okay.
0, L.
Okay.
L. It is L by 2, L.
Yes. So this is the nodes matrix. Then LMs. Somebody.
0, 1.
Yes.
1, 2.
Okay. Very good. Then boundary conditions.
0, true.
That's all.
True, true.
Yeah. We have 3 degrees of freedom. So all the 3 have to give. Then anything else? Force. Force you can tell. What is the applied force?
0, minus p.
No, yeah, so this is node 1, right? So if you see, this is degree of freedom 1, degree of freedom 2, degree of freedom 3. Similarly, degree of freedom 4, degree of freedom 5, degree of freedom 6. This is degree of freedom 7, degree of freedom 8, degree of freedom 9. So how do you say it is 0, 0, minus p? You have at which degree of freedom it's applied?
Second degree.
No, not second degree.
8.
Global 8, right? So it's 0, 0, 0, 0, 0, 0, 0,
0, minus 8, 0.
minus p, 0. This is the force.
Minus p.
Right. This is the force vector. Yeah. Now you can go there and you can do it. So this you can take a screenshot in case you want to type. You can just take a screenshot at this stage and you can do it. I'll stop sharing. Yeah, you can share and you can type.
Sir, how should I start? Sorry, sir, I couldn't get it.
You can share the screen first, then we'll type. You are not able to share the screen, or you are not able to get the. Okay, fine.
I have shared, sir. Here construction is going on, sir. So
Okay.
there is a noise outside and some issues are there.
Okay. Okay. No problem. You go to that copy of, go there and leave the enforced boundary condition part. This part, okay. A, I, E, I have given. Okay. A, I, E, I have already typed in. Nodes also I have already typed. This oh, sorry, it's all already there. Okay. When I tested it, it was there and it's already there. Okay, it's the same, right? It's all the same. So it is as per the values. Okay, you don't have to type it again. I didn't delete it. It's fine. So P is 200 kilonewtons, and that's what I have given. Boundary nodes I have given. And force, I'm filling everything with zeros except f of 7. So f of 7 is the 8th element. And these are all fine. So only thing that is left is we have to enforce the boundary conditions. So go up, go to that function. So what are we doing right now? So for first loop will be the same for I node in bound nodes. You can write that. You're going to every node in bound nodes. No, you don't need to do. You don't need to copy the other two lines. Just say first one for I node in bound nodes.
Yes, sir.
Okay. So in every node you have 3 degrees of freedom. Say okay. So you say node num is equal to I node of 0. So for in bound nodes, what are we having? You're having node number restraint 1, restraint 2, restraint 3. So just say node num equal to I node of 0. That you can copy.
Yes,
Okay.
sir.
Then enter. Then you don't need this. I'll tell what to do. Yeah. So what you should do here, you have to say. So what you need to do is so in every node you're checking the 3 degrees of freedom. So have a loop over 3. So for I in range 3, for I in range 3, or for J in range 3. Range bracket 3, and it has to be together. Yeah, colon and then enter. Okay, so now you can see. So this is fine. Then so what you should check every 3 degrees of freedom, every one of the degree of freedom you have to check. So say you're checking. So you're seeing every. So in the bound nodes matrix, you have node number. So 0th entry is node number. First entry is restraint 1. Second entry is restraint 2, and so on, right? So what you have to do is write. So I plus 1. So you say if what if you don't need brackets. Okay, it's fine. You need a space before that. If space bound nodes. Sorry, not bound nodes. I node. Not bound nodes. We have already checked I node of bound node. So it's like I node. Yeah, actually it is suggesting that I node of I plus 1. Yes. So you understand why it is happening, right? So yeah, it's giving away everything, because I think I typed in the same thing in the morning and then I have renamed it. So it's suggesting everything. So it's actually, so but understand the logic. If I node of I plus 1 means, so I node of I plus 1 is a condition. It's either true or false, depending on whether the degree of freedom is restrained or free. So if I node of I plus 1 is 0, if it is true, then what it should do, it means it is restrained. So the corresponding degree of freedom has to be set to 0. So so you make the diagonal entry k node num plus I equal to 1, and the other entries you are making it as 0. So again, the same logic. So if you're looking at if the node number is node num, then you have node num number of nodes before that. So you're skipping all of them and you're going to 3 times node num plus ith degree of freedom and setting it equal to 0 and all others 1. So similarly, what is the other thing you need to write? So you have set the left hand side equal to 1 and zeros, and what you should do for the force vector? You have to make it 0, right? So f of 3 star node num plus I is equal to 0. That you have to do. Yeah. And then return k and f. Yes. So this is fine. Save it and run it. We'll just run, go to runtime, run all. Okay, so that's an error. What it is? What is the error? You can read the error. Yeah, indent does not match.
Indentation error.
Yeah. So just check that. Is it little ahead or little back that you have to see? Okay, now it's fine. Now run all. Go to runtime, run all. Yeah, again there's an here. What is the error? Value error. Assemble global stiffness. Shape 6x6 and 3x3 are not aligned. Okay. So go to your queue. In element stiffness matrix. Yeah, so Q is not this, right? So
Six
so
cross six.
K dash is 6x6. So you remember what I showed as Q? You need to add 0, 0, 0, 0 everywhere. Yeah. 0, 0. This was the AI suggested thing, right? So it may be wrong. This was, we just took it as it is. Yeah, 0, 0, 0. Here also you can add 0, 0, 0. The last one you can add 0, 0, 0. Okay. Then Yeah, now this is correct. No, it was suggesting the right thing. But how do you get the suggestion again? Yeah. Yeah, I can just accept the suggestion if possible. Just type 000.
Yes, sir, but it is not coming. It is showing, but when I'm typing, it's not showing.
Okay, no problem. Just then type it 000. No, this is wrong. Earlier it was suggesting the right thing, but now it's wrong. So you have to interchange the fourth and the sixth rows. Yeah, 000, comma CS0. Yeah. Yes. Let's check it once because last time it gave something wrong. CS minus SC 000 CS0. Yes, this is fine. Okay, now save it and then run it. Run all. Okay, so it is solved.
Yes,
The
sir.
problem is solved. You can print U. Just type U and shift enter. Small u. Okay, the answer is wrong actually. Yeah, this is not the answer. So there is some kind of some mistake somewhere. Okay, let's see that. It's not a problem. So let us check the values one by one. 000. This is okay. Alpha is fine. Let us see this first. There's something could be going wrong here. So it is for inode and bounds. Okay, come down. I can come down. Let's check the values once. So no, the input values. 1, 2 into 10 power minus 4, 2 into 10 power 11, 4. I think, yeah, this is the same problem as it is. Let me just check if there is some. uh, 3 node plus. Let's do one thing first. Don't enforce the boundary conditions. Go down.
Yes, sir.
No, go down. No, don't do anything in the function. Just go to the step. So you have this enforce boundary condition. This one, right? Just comment that out. Comment it, and comment the next step also. Now,
Yes, sir.
now run it and print k. I'll compare it with my k. So then we'll get to know whether we are wrong before that or after that.
Capital K, no, sir.
Capital K. There's no gap. Don't put a space between print and this. Okay, so we'll see the elements. So your first one is, I'll put it on split screen. So 7.5, 3.015, 1 point minus 1.5 minus 7.5. Okay, that's fine. Then 3.015. This is also fine. Scroll down a little. 000. Then you're having 000. Okay, your the K looks fine. Suppose let's take a random K of say 5,6. Can you print that? You don't need to type print. Just type K of 5,6 and enter. Capital K. Five comma 5. Okay, that's fine. 3 comma 5. Okay, so this is fine. The global stiffness seems okay. Check the local, sorry, the boundary condition. Can you check that? So go to the boundary conditions part. Go to that function. So you are saying, let me compare. So node num is I node of 0 for j I in range 3. 3 into node num plus I is equal to 0, 1, 0. Okay, now enforce the boundary condition and then print the matrix. You're not. What is it? Why does it show? Now it is fine. 1, 0. Sorry.
Initially, I didn't run that part, sir. So it was showing the
Okay.
previous case.
Okay. So you have 1, 0, 0, 1, 0, minus 7.5, minus 3, minus 1.5, 0, 0, 0, 0, 6, 4, minus 3, 8. Yeah, everything is fine. Maybe I don't remember the correct. Let me run my answer and check. Just solve it. We'll see what you get. Print your U. We'll see. U, enter. No, it's. How come K is looking fine? Print your F. F was also fine. You just set F of 7 as P and minus P. F is fine. K, or let's do one thing. I'll just share my K. That how do I share it? Okay, but okay, let's not. Okay, I'll share my screen. You can see if there is some problem, right? I've done
sir.
exactly the same. If you're able to catch it, it's good. But because remotely I can't debug more than a limit, right? So let us see where it could have gone wrong. So this part is fine. The stiffness matrix part is fine. So I have just used a different. The stiffness matrix part we actually have to check. So there could be some. So I used axial freedom as this AE by L and flexural as AE by LQ. So, but that's not an issue because you have taken care to type it as 6AI by L square and 4AI by L and so on. So that cannot cause an issue. This I guess there's no issue. Q is the same. I checked. Then this part is also fine. Returned it. And in assembly we did this. This is okay. Then we had x1, x2, y1, y2. We found the length and inclination. Then this is the assembly operation. So this is the same logic. 3 node plus 1, 3 node 1 plus R, 3 node 2 plus S, 3P plus R, 3Q plus S. Then when you enforce boundary conditions also, it is fine. So I called it as row ID as 3 node num plus JJ. And that has done the same thing. This is the input 1 into 10 power minus 2, 2 into 10 power minus 4, 2 into 10 power 11. L is 4. P is 200 kilonewtons. F I'm setting it 0 except 7. So then if we just solve this, you get U as something. Yeah. In U, the tip rotation has to be 5 into 10 power minus 2 and tip deflection has to be 9.4 into 10 power minus 2. So this I've checked with the manual answer. So this has to match. But I'm not sure where the mistake is. It could be something like indentation or some small error somewhere. Because the indentation had some trouble everywhere. That could have gone wrong. So this you checked, right? Return and for has to be in the same level. In case you don't assemble everything, there might be issues. But that will cause some other, that will not be solvable. The stiffness matrix will be singular. So okay, can you do one thing? If is there a, you can add your.
Okay, sir. I will share it in.
Yeah,
Google.
you can share it on this. Yes, you can share it on this. We'll check that what could have
Okay,
gone
sir.
wrong. But the procedure is the same. There's no. The idea is this. This is the way the. It could be one stiffness matrix element with a minus sign extra or something like that. So that we can check.
Okay, sir.
Yeah, if you can share, we can even check it live. It's some small issue. But again, what I want to show is you can even plot the deflected shape. So we have the nodes, elements, U, which is this solution, and then some scale factor. So you can plot it. Right? Okay, this is printing some unnecessary stuff. I can comment it out. This is not required. So this red is the deflected shape. So this is to scale 1. So this is to scale. This is the actual deflection of the L frame. Which if you want an exaggerated view, you can also scale the deflection. Let me scale it 3 times and you see the deflection more clearly. Right, so this respects the boundary conditions. So the 90-degree angle here is maintained. The slope 0 condition at this base is maintained. And you also have a deflection. So under the application of a vertical load at the tip, you have some horizontal deflection too. So now you can check that this one is the right answer, 9.37 into 3. So so it is simple. This is a statically determinate structure. So what you can do is you can use the so this is a statically I'll give some homework assignment where you can use the same code for more complicated structures. What is this?
Sir, I have
So,
posted.
oh, okay. Let me check. Yeah, I'll do this one first, then we can. So this is the structure. You have force P applied. This is L by 2. This is L. Right. So if you draw the bending moment diagram, what is it? Here it will be linearly increasing. So if you take this as x2 and this as x1, right? So here it is linearly increasing. It increases to a value of PL by 2 here. Then in this span, there is no lateral loading. It only has an axial force and a moment. So this moment will be carried forward. So if you're so confused, you can draw the free body diagram for this. There'll be a moment, equal and opposite moment. There'll be a shear force, equal and opposite. There'll be a normal force onto it. So here the horizontal force is 0 because there's only a vertical force P, which means the shear force in this span is 0. Therefore, it is subjected to axial force and pure bending. So this moment is PL by 2. Therefore, this is also subjected to PL by 2, PL by 2, and the vertical force is P and P. So this you can check it satisfies equilibrium and it's a statically determinate structure. So you don't need any other conditions. So again, you can use our whatever you have been doing since the first session. You can use Castigliano's theorem to see to find the deflection. So we want this point deflection. So say it deflects like this, and this deflection is delta. So this delta is equal to the derivative of the complementary energy with respect to P. So what is this? And complementary energy is equal to the strain energy in this case. So U is what? From bending, it has.
But
Sorry.
sir, we can solve this by directly applying formulas, no sir. No need to use Castigliano's theorem. Just
Okay, if
draw
you have a formula, yeah. What is the formula?
sir, we have drawn the free body diagram. So the vertical component is subjected to deflection because of the moment PL by
Yes.
2.
Yes.
Then theta we know. Theta times L by 2 plus further deflection because of the point load. Then
Okay.
the vertical component is also subjected to axial force P.
Yes.
So it is the total deflection is PL by AE plus
Okay.
theta times L by 2 plus vertical deflection because of the point load.
Yeah, that will be P L by 2 cube by 3 EI, right? Due
Yes,
to this
sir.
point load. Yes, this will be the relative. That is correct.
Okay. The I is 2I no sir.
No, which 2I? I have changed the problem. You didn't notice that. Oh, this. Sorry. Yeah, I made it I. I didn't have it 2I, so it's.
Oh, okay, sir. So it is. Okay. So this will be the vertical deflection at that point.
Okay, so what is theta? Theta is the rotation at this point. Yeah, this is fine. This in this case, this works. Yeah. So theta is what? This is the rotation at this point. How do you find the rotation?
Theta is equal to ml by ei. M is pl by 2. L is L by ei.
Yes. So in case you have a doubt how this one comes, you can say this is this is under pure bending. So it has a constant moment, which means it has a constant curvature. So d square w by dx square is a constant, which is m by ei, and the slope is integrated. You get an mx by ei. So on one end you have slope 0. So when you integrate it from here to here, the rotation at this point will be ml by a, which is pl by 2 by a. So this is fine. This is the right expression. It is pl square by 4 ei. Sorry, it is pl square, pl cube by 4 ei plus this one will give, this is fine, pl by ea plus this is pl cube by 24 ei. So you can calculate EI is, you can say EI is 200 into 10 power 9 into 2 into 10 power minus 4, I guess. That's what I have. 2 into 10 power minus 4. Sorry, 2 into 10 power 4 centimeters per 4. So it is 2 into 10 power minus 4. meters per 4. Similarly, this will be 10 power minus 2 meter square. So we can do this. EI is this. EA is 200 into 10 power 9 into 10 power minus 2. So this is in everything is in SI units. So I'm not writing the units. Everything is in SI units. And P is 200 into 10 power 3 newtons. L is 4. So you calculate this, the answer you get delta as minus 9.3733 into 10 power minus 2 meters. Yeah, so you can do this. This formula helps, but you can do it when you don't have any midpoint span loading or and as long as you can get this right. If you have a distributed loading or a span loading, it might be slightly different. In this case, it's very simple, so you can get this. Yeah, so you can check this value. This is the thing, and as you do this, I will check your. If you have shared it, I'll just check in that.
I have shared, sir.
Yeah, I'm opening it. Okay, so you're looping over all elements. This is fine. This is the plotting part. So this, let me write it in a better format. AE by L, 0, 0 minus AE by L, 0, 12 EI by L cube, 6 EI by L square, 0 minus 12 EI by L cube, 6 EI by L square. And then 0, 6 EI by L square, 4 EI by L minus 6 EI by L square. 0, 2E. This is 6A by L square. That's the mistake. So 6A by. Okay, it says I cannot save changes, but that's basically it. You need it's 6A by L square. You have given 6A by L cube. That's the issue. Yeah, again, this is also, since we copy pasted, this is also wrong. So this has to be 6A by L square. Say 6A by L square minus 6A by L square, 2A by L, 4A by L. Yeah, so this is the mistake. I cannot save it because I don't have the permission to save it, but you get the mistake, right? So that's fine.
Okay.
Anyway, I'll upload the correct whatever I edited. I'll upload my code, and I'll also upload some homeworks. Yeah, but again, we are out of time. I thought today we can finish at least half of nonlinear, but it's not possible. Okay. So the next part is actually important. We have to do some. So tomorrow will be entirely nonlinear. We'll close the linear part today, but you'll have some assignments to do. You can do it. It's not like compulsory, and you're not going to be certificate will not depend on it, but it's, if you enjoy doing it, you have to do it. You can. It's actually important. You have to learn it. In case you have to learn it, such mistakes, some coding mistakes, some indentation errors, some logical mistakes that you can avoid by doing it yourself. So work on it. And tomorrow we'll take up the nonlinear part. And we have 4 hours. We have 2 hours for, as per the schedule, we only have 2 hours. But if you can arrange a session on October 2nd, that will be the last, and we can finish nonlinear to some extent, to whatever extent we can. So
Okay,
yeah.
sir. The same timing or the evening timing, sir? Which time?
Tomorrow?
No, sir. Tomorrow it is morning 9 to 11. In Gandhi Jayanti,
Okay.
I'm asking.
Even that day morning 9 to 11 will be fine.
Okay, sir.
Yeah. If you don't have any issue, you don't have anything else planned that day, something like you have any event on Gandhi Jayanti in your college, then we can have
No,
it
sir.
at some other time. Okay. Yeah, here we may have some events, but I'm not. Yeah, it is just formal, so it's not a big issue. It'll be before 9 here, so it's not a problem. So we can have, it's 9 to 11. I don't have a problem on that day. So yeah, I hope we'll be able to complete module 3 and at least some parts of 4. That's important because So the idea is, until now, you have been redoing the same code for different elements. So the hardest part was doing the assembly for the bar element. Once you did for bar, the logic we can repeat and copy paste the same code for all the cases. Similarly, when you go to nonlinear analysis, this finite element framework will remain the same. You need a Newton-Raphson solver. So the next session will be important because we'll write the main core code for the iterative solver. Then we'll reuse the iterative solver for beam, frame, etc., etc., etc. So again, it will be. But we may not have so many examples as the linear case, but I'll share some content where you can read by yourself and code. But the main part of nonlinear analysis is iterative solutions. So we'll write a code for solving. So okay, let me give a prelude. In general, you have this. Sorry. Yeah. So right now you're solving f is equal to ku, right? In different forms, you're solving f is equal to ku. You're going from element to global or structure, and from structure you're going to reduced. That is, you enforce the boundary condition so that you get an invertible k, and then you're solving this. So here you're solving for u. So this is basically a linear relationship between f and u, right? This is a linear relationship between f and u. So this is a matrix relationship. This is a linear relationship. You have n cross 1 forces. You have n cross 1 displacements, and they are linearly related. So when given f, you can find u as k inverse f when k is invertible. After enforcing the boundary conditions, k will be invertible, and you can get this. But in general, f is a nonlinear function of u. So f is a nonlinear function of u. Right? For example, if you have u1, u2, f1, f2, if you have it as some k11 u1 plus k12 u2 and k22 u2 plus k21 u1, this is a linear relationship between f and u. But however, you can have f1 is equal to tan u1 plus u2 square, and f2 is equal to u1 minus u2 the whole square by 2 plus say some cos inverse of something u2 by square root of u2 square plus u1 square. Right, so this is also a valid relationship. This is also a valid force displacement relationship, but this is very hard to solve. So in this case, if you see, so this relates two forces to two displacements, but the relationship between them is not linear. So inverting this is not as easy as solving a matrix equation, right? So this is highly nonlinear. This is nonlinear, but it is the same. In nonlinear structural problems, we have the force displacement relation in some form like this, right? You can have all kinds. Tan is a nonlinear function, u square is a nonlinear function, square, cos inverse, all are nonlinear functions, right? So this is a valid force displacement relationship. In this problem, if you see, given, sorry, let me make it. So if you have f is equal to r of u, so r is a vector valued function. It is a vector valued function. Basically, r is a function that takes vectors in R2 and returns vectors in R2. It takes or Rn in general. In this case, it takes two-dimensional vectors u1, u2 and returns two-dimensional vectors f1, f2. Now, given u, it is easy to find r. So given u, it is easy to find f. Why? F is just r of u, and r is a known function. This is a known function. Right? So this is it, right? You can substitute in u1, u2, whatever values you have, and you get f1 and f2. That is easy. Say if I said u1 is equal to 0, u2 is equal to 1, you get f1 equal to 1 and f2 is equal to whatever. u2 1 by 2 plus cos inverse of 1, which is 0. So you'll get f1 is 1 and f2 as 1 by 2. But suppose I specify f. Suppose I specify f as 1 comma 1, right? Can we get u? Right? In some cases, we may get. So nonlinear, just as in a linear equation, this is a linear system. If it is solvable, then you can have a unique solution or no solution. Sorry, you can have a unique solution or infinitely many solutions. Particularly if K is full rank, if it is invertible, then we have a unique solution. Similarly, a nonlinear equation may or may not have a solution, and if it has a solution, sometimes it can have more than one solution. So these are the issues that come up when we deal with nonlinear systems. So just as F is equal to KU is the basis for all linear problems, all nonlinear problems have this form. Applied force F is equal to some R of U. We have to solve this. This is nonlinear. We cannot solve in one step, so we resort to some iterative methods. So this we call as external force F external, and this is F internal. And we'll iteratively choose U so that F external, the difference between external and internal forces becomes very small. So in particular, we'll be using Newton-Raphson scheme. Now, if you can get a scheme for solving, if you can get a scheme for this, then you can solve any nonlinear problem, right? Given any R, you can always find U for any nonlinear problem. So that is what we'll be doing in the next session. Yeah, so maybe I don't know how to. So we'll start with this problem, then we'll get to some, then we'll incorporate it into the finite element part. Then we'll see how far we get. Yeah, so we have 4 more hours. Tomorrow 2 hours, 9 to 11. And on Gandhi Jayanti, we'll take 2 hours. So I'll stop it here. I should also give some exercise, otherwise you may not be confident with the coding part. Any other doubts? If you have, you can ask.
No, sir. Thank you, sir.
Yeah, okay. Thanks for joining.
Thank you, sir.
I'll stop the recording here.